Welcome back. We are going to look today at Chapter 15, Conjugated Systems, Orbital Symmetry, and a little bit of UV spectroscopy. And not get into too much of that. So starting right off, this is gonna lead into eventually our benzene ring systems. But in order to understand those properly, we are going to look at first conjugated ring systems, double bonds near each other. And how does this actually work? So we're going to look at what's the difference between an isolated double bond and a conjugated double bond. The idea that a double bond adjacent to another double bond, that just looking at their stabilities, you can tell a significant difference between two double bonds in isolation versus two double bonds uh, adjacent to each other. Because we got this for this chapter, we must consider back to the very end of Chemistry 111. We must think about our when we get into the Lewis structures and you get to hybrid orbital theory, and you got to think of sigma and pi bonds, that all of our double bonds were made by these p orbitals that would overlap and within the pi cloud to make this double bond, and how that these pi clouds, these p orbitals could move and thus stabilize us. So we have these conjugated ring systems. So we're in order to understand this, we can use the simple reaction of simple reaction of double bond plus hydrogen, and we get single bond and energy with like a platinum or palladium catalyst, and we have a delta H of reaction. By looking at these heat we get as a product, we can see how much energy was released when we do this. So, and what we see here is that if we look at, say, a terminal alkene versus a internal alkene, we get more energy out of the internal alkene, because as we know, this is less stable. The internal alkene is more stable, and so you're essentially what? No, well, okay. It's like essentially you find out that the energy related to this, the terminal alkene is less stable. It's the less substituted alkene is less likely to form. Because when you're looking at an energy diagram, you have energy diagram. Remember, we have reactants and we have products. The product on both these reactions are going to be the same. It's going to be boom, boom, boom. So the less stable one is going to be higher up. So you're going to get less energy out. Well, you're going to get more energy out because the delta H of the terminal one is going to be a little bit higher, less of an activation energy barrier, while the internal one is going to be lower starting point. And so, see the energy relation to that. And so we know terminal alkenes are less stable than internal. Well, if we look at isolated double bonds, we look at this. If I say this guy has, well, look at this. This guy has the energy. We'll just call it delta H of 1. Well, with the two double bonds, if I look at this, the delta H of this guy, I'm going to call it delta H2, is approximately equal to delta H1 plus delta H1. Isolated double bonds are essentially the enthalpy of the reaction is essentially equal to the sum of the loss of our two double bonds. Now, if you considered something like this, where we have internal and external, you would have delta H for this 3 would be equal to our, we'll call it delta H I plus delta H T, our terminal versus internal, but we could essentially sum them up. The big thing is that they're isolated. We just get the sum. When we look at a pair of conjugated double bonds, however, they are far more stable than the isolated, and we cannot predict, we cannot simply get the sum. So, that in mind, so if I have this structure, double bond, so, and we look at the delta H of that guy, delta H of this guy, it's going to be greater than the delta H of the internal plus the delta H of the terminal. This is far more stable. Now, on the other hand, cumulines, which are cumulated dienes or allenes, where the alkene is right adjacent to the alkene, such as CO2, for example. Like if I did this, then 1, 2, 3, 4, 5. Yeah. If I did this, the delta H in this case would be actually much lower than the sum of them, because this is actually less stable than our isolated double bonds. So if we look at our stability, on the lowest we have cumulines, followed by our terminal alkyne, followed by internal alkyne, followed by iso terminal dienes, then followed by iso T/I dienes, then conjugated diene. Okay. Now, the question is, what causes this stabilization? What causes this stabilization? That why is the conjugated diene far more stable than, say, an isolated dienes? And this comes from the pi bonds in the p orbitals and the conjugated. There is a resonance that occurs as an electron is delocalized and the bonding of all the atoms ends up being averaged. So if you have a 1,3 diene, you have an average of the electrons moving from the 1 to 2, the 2 to the 3, and 3 to 4, 1,3 diene. So we're going to actually look at some molecular orbitals. So when we look at a p orbital, you should remember, had two phases, the positive phase and the negative phase. And this is not actually a charge, but we're just using the plus and minus for the phases. If you see it in a diagram, you might have one being shaded and one being not unshaded. We're going to just use plus and minus to save my little fingers. But generally speaking, bonds can only occur between the same phase. So if I had two plus phases, we can bond. If I have two minus phases, we can bond. But the one thing we cannot do is bond between a plus and a minus. So we can break things into two types of bonds. Our bonding phase, our bonding molecular orbital, which is constructive interference, constructive overlap. So erase the shading. So constructive interference is going to be when two pluses are adjacent to each other. These are going to be our pi bonds. And then we have where we have destructive interference, where the two phases are opposite to each other, and in which case we would have an antibond, a so pi star. These are going to be higher energy. When we look at this, these guys are going to overlap. We're going to see bonding up top, bonding in the middle, bonding below, because these guys are going to bend in to approach each other. Now, antibonding, they're going to be bending away. They're repelling each other. So there's actually the farthest thing from bond. If you're looking at here, we're saying they don't want to speak with each other. So, and in this case, this results in a node, a region of 0 electron density between these two carbons. So as we give more and more bonds, we're going to see more and more nodes. So let's look at 1,3-butadiene. 1,3-butadiene, we can have three different types of densities, three different types of bonding overlap. We have so looking at all of our p orbitals, plus, 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 plus. So that means all the other ones are minus. So shading here is we're going to call that pi 1. That there's no region of electron density of there's no nodes in that structure. Excellent. This one's going to be called pi 2. We're just numbering them. Plus, plus, and plus, plus. We have a bonding here. We have bonding there. So we have essentially a region of no electron density in between. We have one node for our pi 2. And continuing down. Shoot. Shoot. Okay, do that again. So for our pi 3, we're going to have two nodes. Put a plus down here, put a plus down here, plus up there. So we have a region of bonding here. Node right there. Node right there. And then finally, for the last one, pi 4, you're going to have as many different orientations as there are p orbitals. Plus, 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 plus. We in pi 4, we have 3 nodes. All of the bonds are anti-bonding. There's no overlap of our p orbitals. If we're putting a molecular orbital diagram, boom, 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 we have our 2 bonding orbitals, pi 1 and pi 2, and our 2 anti-bonding orbitals, pi 3 and pi 4. These are going to be our anti-bonding orbitals. Looking at that, how many electrons are going into these pi bonds? We have 4 carbons. Each one is giving 1 electron per pi bond. So we have 4 electrons to put in. So we'd put in lowest energy and pair them up and moving on up. So what do we look at? We see that these guys are stable. We have these guys only in the bonding orbitals. That these become stable in the planar configuration. That now looking at these, but that pi 1 is particularly more stable than pi 2, but we have here is that, okay, let's go to, well, let me erase some stuff. So we can look at some of this. We actually see in the structure, you could have a cis versus trans butadiene. That the trans is 12 kilojoules more stable than 29 kilojoules, I think, if I wrote it down right, more stable than the, it's 12 kilojoules more stable, but it could undergo a, use lower, but a 29 kilojoule interconversion to a cis. And that is because we can convert our pi 1 to the pi 2. Essentially, in the pi 2 structure, we can see in pi 1 structure, there is no free rotation allowed. In the pi 1 structure, there is no free rotation allowed because as soon as you break up that free rotation, as soon as you rotate at all from that structure down there on pi 1, you no longer have a complete uninterrupted break. Though you can easily convert this with 29 kilojoules to break over the energy barrier to get it shift this into the pi 2 bonding structure. This pi 2 bonding structure, there is a free rotation because you have that node in between carbon 2 and carbon 3. So this can easily rotate. Even though the trans is more stable, we can shift into the cis. And then it can readopt our pi 1 configuration. So we can also do this. We also see the stabilization with allylic cations. So cations and radicals are stabilized through this delocalization process. So we can look at like this allyl cation. And versus, let's see, versus, say, this. That if we look at cation stability, we have our methyl cation is the lowest, of course, our primary, our secondary. Now, the secondary, however, is approximately the same energy as an allylic cation. So even though this is allylic is technically a primary cation, it is similar to a secondary in that the delocalization will stabilize this. And then if we get a tertiary is similar in energy to an allylic a secondary allylic cation. So they're similar in energy. That allyl group is essentially like having a secondary carbon attached there. Now, this stabilization, this delocalization will also explain a really weird property of adding the hydrobromic acid to dienes. That when you add hydrobromic acid, you can see to the structure. If I take this, you with HBr, you're going to see both 1,2 and also 1,4 addition. 1,2 addition and 1,4 addition. So you're going to get two products. You're going to get bromo 1,2, and you're also going to get 1,4. Now, and this is a Markovnikov addition. So it's a Markovnikov addition. So how do we explain this? I mean, the first step is the same thing you would have done when you would have done adding HBr to an alkene. But the conjugation, that's where it gets a little different. So let's start. Mechanism. We have H, we have Br, we have the diene going and attacking there and kicking off our bromine. And we're going to make a cation. Now, H. Remember, Markovnikov, the H goes to the least substituted species. So where we're going to make the cation, you're going to make the more stable cation, which is the secondary cation. In fact, this is an allylic cation, so it's even more stable. Now, depending on the speed at which this reaction occurs, this is going to undergo a delocalization. Now, this is not necessarily the most stable. This guy is the most stable, the middle guy. Our secondary allylic cation versus the Allylcation over here. But however, depending on where that bromine is and how fast this bromine attacks, we can either attack there at the 2 position or there at the 4 position. And so you can get both products. This happens with conjugated dienes. You can actually control which product forms through what's called a kinetic versus thermodynamic controls. Kinetic, remember, has to do with speed. Kinetic property is a fast reaction. Thermodynamic is we form the most stable. So dynamic. So you form the most stable, the one that's going to, it might not form right away, but given enough time, it will form. So kinetic, you're going to do everything you can to make the fastest one form. Kinetic, you say you run it at 80 degrees C, or at negative 80 degrees C, so only this guy has lower activation energy, which is why it's kinetically favored. This one has lower delta A energy of products. So higher delta H reaction. So we're going to get more energy out of the thermodynamic, but there's a higher energy barrier to get there. So if I do a negative 80 degrees, see, we're going to favor the 1,2. It's going to form the kinetic product. If I run this instead at 40 degrees and give it enough time, we're going to form the 1,4, which is the most stable. Remember, why is that most stable? Because internal alkenes are more stable than external alkenes. So if you can rearrange that to form an internal alkene. Yeah. But why is there a lower activation barrier for the kinetic? Because remember, our allylic cation is more stable. In the end, it's higher energy product, but more stable intermediate. So you have to have time to shift to the higher energy intermediate prior to attack. So from our center position where we have our so from this center position, we have a lower energy barrier for the kinetic. We have a higher energy barrier, but it drops down lower for the thermodynamic. So depending on how you control it. So the idea about running this at low temperature is you're less likely to reverse the reaction, get back to this intermediate, and thus making this product. If I can't jump over this high barrier here, then it's only going to form kinetic product. At 40 degrees, that yes, you're going to form kinetic product faster, but you're also going to form thermodynamic product faster. 40 degrees, we should be able to reverse this reaction and get it back. And if we reverse this reaction, we can get it to this guy, which it's much harder to reverse and less likely to reverse once it's formed. So at equilibrium, we get greater amounts of 1,4. Now, so something to keep in mind when you're dealing with dienes. There's ways to form allylic radicals by using a bromine in certain conditions. If we use NBS, which is a radical initiator, bromine and light, H nu, what we can get is the single addition of bromine adjacent to the alkene. So what's going to happen? So the mechanism is first the bromine is split by the light to form two bromine radicals. The bromine radicals then attack our alkene. Attack alkene to make a allylic radical. Just like a allylic carbocation, this is particularly stable. Because we can essentially, in this case, from here, we can have some exchange. There. And then that can further attack more bromines and chain this on. So make a product. Now you could also do this with chain this on. And of course, HBr, which is the byproduct of that one of the first steps, can then go mix with NBS to form more Br2. But okay, when we look at allylic radicals, it's like more Br2, and it forms the NBS is our and form N H. Now, when it comes to allylic radicals, stability is very similar to allylic cations. We have the methyl radical, the primary radical. Well, it's a little different. The secondary radical, the tertiary radical, and then you have your allylic radical. And the allylic radicals approximately the same energy as a benzylic radical. And then essentially you have what we have in a shift is we have a bond. Half of that electron is half of that lone pair is going down there, and half of it's splitting over there. As we're shifting over, we're only having one p orbital going. Now, if we just added Br2 to this reaction, you would just add 2 bromides to be a dibromo compound. But Br2 with NBS tames this to allow for our single addition of bromide. So if I did just Br2 and plus HV with a boom, 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 what we're going to get is, sadly, Br, boom. But when I add Br2 and NBS, that's where we get the allylic radical. Okay. Now, continue on the same scheme of things. How does the molecular orbital look like for this allylic radical? And how the allylic cations. So we have 3 carbon groups. So we have our boom, boom. We got our first one, which is all bonding. We got, which is lower in energy than. Now, in order to do this, we have a node right in the center. So we have a non-bonding MO. Non-bonding. This is different from our anti-bonding. This is our pi bonding. We have a non-bonding because we have same as an isolated p orbitals. So it's non-bonding. And then the anti-bonding. So in this case, we have 3 electrons. Put them in. 1, 2, 3. We have 2 in the bonding, 1 in the non-bonding. If I look at the allylic, cation, would have 1 electron left, 1 electron less. So with a cation, so that's a radical. That's with the cation, 2 electrons in the bonding. And if I had an allylic anion, we'd have 2 electrons in the non-bonding. So when we see allylic halide and tosylate, we see a SN2 displacement of these guys. They're activated when we see the displacement, SN2 displacement of allylic halide or allylic tosylate. This occurs through the activation by the p orbitals of the carbon, thus lowering the activation energy of the transition state. This allows some reactions to occur, such as Grignard and organolithium. So let's just look at this. So if I have this bromine, H, and nucleophile attacking there, essentially what's happening? Well, what's happening is in this transition state, in a standard one, we have a plus, minus, and attacking my bromine. The nucleophile has to come in and kicking this out. To make our new bond. Now, in the case of allylic, so boom, 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 H. We already have essentially this. Plus, I have this. So when the nucleophile comes in, and adopts that transition state, the transition state, we can adopt, this is going to be much lower energy because we already have these p orbitals. So we can adopt our all bonding p orbital. Making it much easier for the nucleophile to come in. So a much lower energy transition state, stabilized by these bonding orbitals. By this bonding orbital. Lowering the energy means it's easier to kick them off. So that's going to be where we're going to stop. We are going to continue this chapter by looking at what's called the Diels-Alder reaction, which happens to be 4+2 cycloadditions. We're going to take a diene and an alkene, combine them together to make a new cyclic ring, typically being about a 6-membered ring, and and this is caused by the shift of these bonds within these molecular orbitals. And we'll look more at that next video.